Hello, welcome to the Second Life lithium iron phosphate e-bike battery pack rebuild. My name is Marcel, AI6MS, and let's get started. First off, this is me. I'm Marcel, AI6MS. I was licensed in 2008 as KI6QDJ while I was a student at Cal Poly San Luis Obispo studying for my master's in electrical engineering. These days I'm very involved still with the Cal Poly Amateur Radio Club, Cupertino Aries, and with the Salinas Valley Repeater Group. In my day job, I design batteries and charging systems for consumer electronics products, and in my free time, I love playing with batteries. So my slides and videos are available at my QRZ page. You can reach out to me via Twitter or on my YouTube as well. So hopefully you'll enjoy the presentation. So today we're going to be talking about converting a lithium iron phosphate battery, a used e-bike battery in this case, into a 12-volt amateur radio friendly battery pack. So we'll talk about kind of how I got the batteries, doing a little bit of background and debug on them, how we rewired the pack, some modifications to some of the peripherals and features on it, and then the final testing of the pack and how it performs to some other packs that you might buy new. For some other information and a background info on lithium batteries, I have some other presentations that go into a deep dive into lithium iron phosphate chemistry and why it's such a great choice for amateur radio. And feel free to check those out on my QRZ or YouTube page as well. All right, first off, a little bit of safety. Batteries are inherently dangerous, lithium batteries particularly. So this presentation is not qualifying anyone here to perform those tasks. If you're taking on a battery project, please make sure that you know what you're doing, that you're properly trained, that you have the right personal protective equipment, and yeah, just be careful. So especially with used batteries, just be extra safe because you don't necessarily know their history, and just want to make sure that you're taking the necessary precautions. Okay, with that out of the way, battery use. Reuse is really, really cool. So in the electric vehicle market, batteries and even in consumer electronics, batteries are typically considered end of life when they're around 70 or 80% capacity. So typically, if you look at manufacturer's data sheet for a lithium iron phosphate battery, it'll say like after 300 or 500 cycles, it's got 80% capacity left, and then we don't guarantee it past there. For electric vehicles, for example, like e-bikes or cars, often once those packs hit that sort of capacity limit, they don't perform as well. So you can't accelerate as quickly, they get hotter when you charge them, and they just aren't as exciting for the customer. So typically they want to use them for some sort of what we call second life application. That might be grid storage, or in this case, amateur radio. So in this presentation, we'll be talking about these e-bike batteries that I got my hands on. There's a pile of them here below, these 9 batteries that I picked up, and specifically the lithium iron phosphate ones. So a lot of these e-bike batteries, like these bottom 2 here on the right, those are using standard lithium ion 18650, as lithium ion chemistry. The rest of the ones here are all lithium iron phosphate, which we particularly like for amateur radio. So we'll be focusing on those in today's presentation. All right, so when you get a used pack, or why is a pack no longer being used for its original purpose? Whole bunch of reasons. Pretty commonly, they have a failed BMS or battery management system, where it's just a cheap electronics board in there, and if it failed for some reason, it'll usually fail safe and prevent you from using the pack for anything else. Other common issues are cell over or cell under voltage protection that kicks in. So that's where the pack has a condition where one of those cells went too high or too low in voltage, and then it went into a safety protection state. Under voltage is pretty common, especially if packs are used very heavily or develop a short condition, or if they've been sitting on the shelf for a really, really long time, they might just have depleted. You could also have just simply a blown fuse where someone used the battery too heavily or tried to pull too much current from it and it blew a physical fuse. Or you could have physical damage, which you want to be really careful with, right? So if there's physical damage, that is a pretty big concern and likely not a pack that you'll want to reuse unless you remove the damaged cells from that. So if you get your hands on some used battery packs, it's really up to you to inspect and decide what you're going to do with that. If you're going to reuse it or take it apart or dispose of it, recycle it somehow. The first one is obviously do a voltage check. In this case, top left right here, you can see this pack is normally a 38 volt pack and it's sitting at around 16 volts. So that's a less than happy battery pack, but it still had battery voltage at the terminals. So that's a good sign. It means the battery management system is functioning. You could run a capacity test on the packs as is and see how much capacity they have. Maybe you don't want to spend time on a pack that only has 20% remaining capacity. So there are a bunch of different options there that you could think of for how much work you want to put into it. Other simple ones, you could check the fuse, of course, like we said. In this case, these packs have a nice little removable fuse module here that you could just pull out and take a look at. And then history is also important. So usage or storage conditions could tell you if it's worth reusing this battery. If the battery's been abused and being used at high temperatures and high currents a lot and being stored at high temperatures, it'll likely be much more aged and not have as much capacity remaining or usable life left. So those are things you can test again with the capacity test, or you might have a clue. Like this battery pack right here had a capacity test performed on it back in 2017. So that pack was at least 4 years old. And that's a good data point to know that packs also have a finite, or cells also have a finite shelf life. So that's just something to think about. And then lastly, damage. I mentioned this on the last slide, but it's really important to think about this hard, especially for an e-bike battery that might have been rattling around on the back of a bicycle for a long time. When you open it up and inspect it, it's really important to look closely and just see if there's any physical damage that you can tell. And if you're unsure, better to be safe than sorry and just pass on that pack, get another one. So here's one that we opened up. This is a 38.4 volt, 9 amp hour Prodeco Technologies battery. It has a really nice voltage meter on top, which is kind of cool, and a little tail light in the back as well. And you can see on the inside there's a lot of foam padding, right? So with pouch cells in a e-bike situation, they actually had almost a centimeter of foam on all 4 or all 6 sides of that battery pack just to make sure that it's well protected on the bicycle. And that's just shock and vibration conditions from being on a bike, something to keep in mind. Other than that, this pack is very nicely laid out in the inside. Right, these are some of the connectors on the front, nice silicone wire. This is the battery pack when it's removed, barcodes and some labels on there with capacity ratings as well. And then the old battery management system attached here to one end actually has some info on it, 5 amp charge, 15 amp discharge, 36 volts, some no-name brand, and yeah, it was actually still working. I wasn't going to use this BMS because it's for a higher voltage, so I took that apart a little bit further, took off the heatsink and took a closer look. It's really interesting to see there was a little bit of water damage on this, which is surprising because it's inside the battery pack, but that just goes to show how usage and storage conditions are not always straightforward. So definitely something you want to think about when you're looking at these packs. All right, so next up is rewiring the pack. So we talked about this pack as a 38.4 volt, 9 amp hour lithium iron phosphate battery. And the actual cell configuration on the inside is 12S2P configuration. So that means there are 12 sets of cells in series, and you can see these red wires are connecting each set of cells in series, and then 2 in parallel. So each of these is actually 2 cells in parallel, and then that connects in series with another 2 cells, which connects in series with another 2 cells, and so on and so forth. So you can see there are rows of 3 here, and there are 4 sets of those. So it's 12 in total that gives you this 38.4 volt nominal pack. So if we do the math on that, that's 24 individual pouch cells, which are normally 3.2 volts for a lithium iron phosphate. And for a 12 volt amateur radio use, we want to reconfigure that into a 4S pack. So we want 4 strings in series. And since we have 24 cells, that would be 6 in parallel. So it's a 4S 6P battery pack as shown here. That gets us a 12.8 volt nominal cell voltage or nominal pack voltage once you have this pack fully built up. So first you need to take it apart. Here are all the old balance leads. You can see each individual cell has a tap on it, a voltage tap that goes back to the battery management system, and just slowly peeling back all the layers to expose the individual cells. Really important to do this carefully. You can see how much Kapton tape is here just insulating all the terminals. Really critical not to short anything. So here in the top left, as I'm starting to desolder each of the old leads on there, I'm always covering up all the cells underneath, or as I'm removing solder from one, putting electrical tape over it here as well, just to make sure you don't have any shorting conditions. All it takes is one of these wires to short across one of these cells, and it gets a pretty dangerous situation very quickly. So do this carefully and make sure you are very, very meticulous and paying close attention while you're doing this. When I had the cells all disconnected, so all the leads were removed, I didn't actually have to reconfigure the physical pack, which is what's really nice about this conversion. I could just leave them as exactly as it is, and then add bus bars across it. Since I was doing pairs of 6, right? We said 4s6p. The 6 parallel cells are right next to each other, so we can just run one piece of tinned copper wire across those cells and carefully solder onto all the leads that were already soldered from the previous joint. So it's actually a really nice way to do it. While I had the packs all apart and the cells were just in pairs of 2, I went ahead and checked all the individual cell voltages as well. They'd been sitting for a little bit, and they were all within about 5 or 10 millivolts of each other, which is great. So that shows the pack is actually in pretty good condition. Sometimes you'll find that after you take the cells apart and they sit there, some packs might have much higher self-discharge, and they'll start drooping pretty quickly. If you have the option, you might want to rebuild the pack, take apart the pouches and separate them from each other, and then just pair up the good pairs with each other and create one new pack. So that's just some things to consider if you're building a new pack here. So once we finished rewiring, this is what it looked like. Again, we did a 4s6p, right? So here's our main battery negative, and then we've got the positive of that set tied together with the negative of the next set. And then again, 6 cells tied together there, and then the tail end here all the way up to the positive end. And then you can see each of these individual red balance leads all going back to the battery management system here on the end, with then the negative output that goes to the connectors on the outside of the pack. So this is what it looked like. Run a couple tests here real quick, make sure all the voltages look good, make sure the battery management system kicks in, and that's pretty cool. A quick word on battery management systems. These are absolutely required. I do a little bit more of a deep dive in my other presentation, but high level, you need to have one. These manage over voltage, over current, over temperature protection on the packs and make sure that the cells are never put in an unsafe situation. So absolutely critical that you include one. Since we removed the old 38 volt one, we now want to put in this 12 volt BMS, or they call it a 4S BMS since we're using the 4 series cells. For this build, I used a brand named Dali, so Dali BMS. They make some pretty low cost and very high quality. They're actually nicely potted, rubberized enclosures in aluminum, and they're great. You can get a 20 amp one for just $12, and they work really well, come with the balance leads and everything. The 60 amp version is just twice that, so $24, and that's a really, really effective way to get a pack built quickly and safely. If you want to take it up one notch, you can get their Smart BMS. I just got one of these and I'm starting to play with it. It comes with a little Bluetooth module. The main unit is a little bit bigger because they have the Bluetooth module, the Bluetooth interface and some other smarts built in, and it's quite a bit more expensive. So it's about $48. So it's again twice the price, and then you're adding another $12 for a Bluetooth module. But it's a fun little tool, and you can show your battery capacity to your friend. I've used other smart BMSs before on my other battery builds. This is my first time buying one of Dali's. Excited to try it out, so those are pretty neat. Key thing here is that you want to size the BMS for the cells you're using. So if your cells are only capable of putting out 10 amps each, and you have, let's say, 6 in series, that means that this pack could put out 60 amps, right? So then you want to make sure that your BMS is at or below 60 amps. You don't want to, or that it cuts off at that stage. You want to make sure that you're never able to pull more than your pack can take. And ideally, if you can set those parameters, you can configure them. So the smart BMSs, the really nice thing there is you could actually oversize it so that you have more FETs and you have lower series resistance. But you can then configure the actual cell voltages, the high and low voltages. You can configure the capacity and lots of other things. So that's been kind of my preferred way to build packs, just because I really like having the control over the battery management system. But most people will probably find that a regular, the $12 BMS will do the job perfectly fine. So yeah, that's kind of my spiel there. There are no-name options out there. You can get way cheaper. You can get $4 or $5 BMSs. I wouldn't recommend it. The couple dollars more that you'll pay for a Dali that's known to be pretty good quality, and a lot of people are using those successfully, I would just go with that. So that's my simple answer. All right, so now for the fun parts. So this battery pack, it being an e-bike battery pack, has some cool features on it. So it sits on the back, on the trunk of the bicycle, and has a little tail light on it. So you can see this little red light with a little button that you click on and off, and it turns on these 5 red LEDs. So I was like, this would be really cool to keep in the pack, just a nice little light source, for running at net control or in your shack, or just as an emergency light for the battery pack. So I wanted to see how we could convert this to 12 volt. So originally it's about a 15 milliamp drive voltage or drive current for the LEDs using a 2 kilo ohm resistor, and that's designed for kind of the 40 volt pack voltage. So that's the board here in the bottom right. That's what it was. You can see it's a pretty hefty resistor. It's about a half or 1 watt resistor, I think, because it's burning about half a watt of power for current limiting, given the amount of voltage drop. So that's pretty significant. But when you run the numbers for 15 volt pack to keep it around 15 milliamps, it's around 333 milliohms or 333 ohms and less than an eighth of a watt of power dissipation. So you can see here's the modified one with the smaller resistor. Just dropped one in there that I had in the shop, and it works great. Very easy mod. Change out one resistor, make sure the math is right, and then you have these LEDs. They change the brightness a little bit depending on if the battery is fully charged or not fully charged, but we don't care. It's just a simple tail light and a really cool way to just have some light on the pack. So the next cool part is the capacity meter. So the capacity meter sits on the top of the pack and is just a one push button. So you literally take the pack and then there's one push button on the top, and it turns on the lights to show you what the capacity is. So that's really cool. Again, this was designed for the higher voltage, the 12S pack. So I took this on the bench supply and just swept through to see where the voltage set points were, and its operating range was about 27 to 41 volts. So as expected for the higher voltage range, but it just uses a simple LM324 quad op amp. It's actually only using 3 of those op amps to then drive the 3 LED outputs for the red and the 2 green lights. So this one was a little bit trickier. I wanted to figure out how can I adjust this and make sure that it works for the set points that I want for 12 volt for the 4S battery pack. So this took a little bit of reverse engineering. This image on the right is kind of a conglomeration. I took a picture of the front and the back of the PCM of the circuit board and overlaid them so that it effectively was like a layout program, and I was looking at it, and then I wanted to pull the schematic out from it. So I started tracing out all the nodes, writing down all the resistors and their values and where the LEDs were and where everything connected, and was able to pretty much get them all figured out. Writing down the resistors and the tolerances, what voltages I'm seeing at different nodes, the reference zener that they had for a 2.5 volt reference, and then all the nodes that everything was connected to. So I just started naming the different circuit nodes and then throwing it onto a little schematic. So simple schematic just on a notebook, input voltage, goes and drives the voltage reference, and then you have the main voltage divider that feeds into the comparator. And this is really the key one. You have your 3, 2, and 1 output, which was for your red, green, and green LEDs. So looking at this, I plugged this into a nice little spreadsheet and figured out that R4 is the one that we can tweak and have the values work out the way we want. So looking at it here, in the original 12S state, at 27 volts, all the lights would be off. At 27.7, the first light would come on. 35, the second light would come on. And 41 volts, the third light would come on. And then when I plug in 19.5 volts, those set points scale down very nicely for the same thresholds, but at a 4S voltage, which is great. So we did that here, and then those were the voltage thresholds. And I checked that against the per cell levels, and that was pretty much the same. You can, of course, tweak these if you want to. If you wanted the voltages to, the LED bars to show different voltages or different levels based on a different voltage threshold, you could change it, of course. Spreadsheet's pretty easy to make. It's just a voltage divider. In this case, I said, well, we might as well just use the same thresholds that they had, so the same per cell voltage thresholds, and just scale it down. The nice thing is I happen to have a tin of 39 kilo ohm surface mount resistors sitting in my shop. Of literally randomly had this tin, and as a result I could just use those and put 2 of them in parallel onto the circuit. So nicely stacked them here, just one on top of the other into the R4 position, and voila, the circuit just works at 4S, and it's really sweet. So now the same pack has just a voltage meter on top of it. A very handy little feature. Go press the button real quick, convince yourself that it's got full voltage, and then go out for a field day or to SOTA or whatever. So it's a really nice way to just get yourself some confidence in the system. Okay, and then the finishing touches to the pack itself. Top left here, this is doing a test fit, making sure how everything fits in there, how the wires all are going to route in, where I want to put connectors and stuff. This is before I wrapped all the foam back around it. That was pretty critical, but it all fit in there quite nicely. The really neat thing is how I could fit the power pole mount. So it was just like within a millimeter was the right size. I could fit this 2 power pole panel mount from PowerWorks into this spot on the bottom of the battery pack. And it's right next to the original blade connector for the actual e-bike on the back of the bicycle. And that fit perfectly. The other really nice one is I was able to put a 30 amp thermal circuit breaker right where the old fuse mount was. So there was a 10 amp fuse there before, was able to pull that out and then put in a higher current thermal breaker. Same spot with the nut, fit beautifully. So this is from the inside, you can see just running wires here between this is fused on the positive side, and then the BMS is sitting on the negative side. So just a little bit of extra safety. Disconnected all the other ports. There's a charge port on here as well that I didn't end up using. You could plug it up if you wanted to, but it's just not hooked up to anything, and that works out pretty nicely. Of course, we have to hook up the peripherals as well. So we had the voltage meter here. This is on the top of the unit, and then the tail light, the red tail light, of course. Got to have all those blinky lights on here, and have those wired in to the power pole output as well. So those will be downstream of the fuse and downstream of the battery management system as well. So if anything goes wrong with the battery, both of those will stop working, which is exactly what you want, so you don't over discharge the pack. Here's all the foam put back in place, everything taped up nicely. And then, of course, put some stickers on it, because we all have stickers laying around and never know what to do with them other than put them on your laptop. So I thought it was great to just put a bunch of stickers onto the outside of the battery pack. So, Ham Study sticker on the top, and Arc Electronics, a friend of mine, an ARRL sticker, and what else do we have? Some more ARRL stickers, a DX Engineering sticker. There we go. They were also helping out. So it's pretty fun to just put those on there. And then the really important one is all the labels on the bottom. So labels and specifications, this is just really helpful to have, especially if you're building something from scratch. If it's, a bespoke little system, you want to make sure that you remember what it is. So a couple months from now, when I pull this out of the garage and say, hey, what was that? How did I build it? What are the specifications for it? Making sure that you have that available. So this one says on the bottom, 22 amp hour, 12.8 volt lithium iron phosphate battery, made by Marcel, December 2020. It's a 4S6P pack with a 40 amp DALI lithium iron phosphate BMS and a 30 amp thermal circuit breaker. So that's critical. That tells me what's in there, reminds me what kind of BMS I used, what the specifications are. I can go look up that data sheet for that BMS and make sure that I remember how this one worked. And I also put the recommended charge on here, so 14.5 volts at 4 to 6 amps tops. And then the tested capacity that we tested it at the end of 2020 with 22.5 amp hours at a 2 amp discharge. So that's a pretty important thing to put on there. Highly recommend everyone buys a label maker if you don't already have one. It just makes all your projects a little bit more organized and easier to figure out in the future, both for yourself and for anyone else that you might give it to. Okay, and then lastly, we're going to do some charging and testing out. So once you've finished reassembling the pack, fully charging it to the top of charge and allow it to balance completely. So balancing is where you allow the cells to get to the exact same voltage, and the battery management system will do this automatically at the top end of the charge. So it's called top balancing when it's usually above like 80% capacity. And you'll want to let it sit there. So it's the first time you're doing it for that pack, and the pack's been sitting around for a while, and the cells are hooked up like this for the first time. Let it sit at least overnight, maybe a day or two. You can always check the cells individually and just see once they're all stable and comfortable, then you kind of are good to go. I then ran a capacity test. So here's my little West Mountain Radio CBA4 computerized battery analyzer. Great little system, absolutely love that unit, and use that to run capacity tests. So I ran 2 different capacity tests, one at a 2 amp discharge rate, so kind of a lower discharge rate, and then at a 10 amp discharge, so a much higher rate. That's more if you're transmitting on a mobile radio or on a HF radio. Those 2 numbers together will give you an idea of kind of the health of the battery and the overall capacity. So the green line here, this is the 2 amp hour discharge, and we got down to about 22.5 amp hours of total capacity. So that's pretty good. It's about 83% of the original capacity of the pack, or the cells, I should say. And then at the 10 amp discharge, you can see obviously the voltage is lower at that point. And then the discharge is a little bit steeper here because it has a little bit more internal resistance. And it ended a little bit less, so around 22 amp hours, about 82% capacity. So all in all, 81, 83% capacity in that range. It's pretty good for a used pack. And this definitely performed exactly as I expected. I was pretty happy that it still had, more than 80% usable capacity left, and that works out pretty well. So if we compare this back to a normal battery, so a normal 20 amp hour off-the-shelf battery would be about $200 or $193. This BioEnno one, I actually own this battery as well. That's a pretty common one that you would have. For this pack, I spent $42, and most of that was on a power pole mount because those are expensive from PowerWorks. The thermal breaker was $6 off Amazon. The BMS was $16 off eBay. I think I got it shipped with some other stuff as well. And yeah, that actually works out pretty well. I should put a little plug. After I did this project and started buying some to build more batteries, I found this guy called the Crazy Ham on eBay, and he makes these little 3D printed single power pole panel mounts for about $3.50 if you buy a couple of them from him. Really cool. I just bought some. I haven't used them yet, but it's a great little way to support small businesses and also to get a cheaper solution for just getting a single power pole, because you don't usually need both. Depends on how you're using it, of course, for your setup. But for like a simple SOTA activation where you just need one port, that might be sufficient. So thinking about lifetime for this pack, so lithium iron phosphate batteries typically have 3,000 to 5,000 cycles of capacity, depending on how they're discharged and how they're used. So if we have about 80% tested capacity remaining, or 83%, I think we said. On this graph, this is just from some website, PowerSonic, they have kind of a remaining capacity versus cycle life. So if our remaining capacity is here around 82% or so, we've got about 2,000 cycles used, right? So if it's got 3,000 to 5,000 cycles total, somewhere about half of it is probably used up. Depends on how aggressively it was used before. But I'd say that's pretty good. So 50% usable life, and you still have 22 amp hours of capacity left right now. So for a battery that was otherwise going to go into the trash or get thrown away, that we can get several more years. And honestly, I don't think I'm going to be using a couple thousand cycles unless I put this into an off-grid solar application. I'll probably be using it a couple cycles a year, maybe a couple cycles a month if I'm actively doing something. So this will last plenty of time, and that's a really cool way to just reuse batteries. So super exciting. I did want to give a big thank you to Joel W6TC for giving me these batteries. He called me up after he saw one of my other presentations and said, "Hey, I've got a bunch of e-bike batteries. Would you like to use them?" I said, "Absolutely. I'd love to play with those and try this out." He also runs a small business, so just like the Crazy Ham guy, if you like supporting small businesses, he runs this company called Western Active. I just replaced my tower climbing utility knife with one from his website. Really cool, bright orange, and attaches to my lanyard, so when I go do my tower climbing, it's a great way to have a nice new knife and replace my 20-year-old one that was on there before. So hope you enjoy this presentation. All my slides and videos are available at my QRZ page. You can reach out to me, ai6ms@arrl.net. And a little plug just for people wanting to get their licenses or upgrade their licenses. Fully remote amateur radio exams are a thing. You don't have to wait for in-person. During COVID, it's no problem. hamstudy.org/sessions has all the sessions being hosted. There are dozens of ham sessions being held a week, multiple every single day. So there's no excuse to not get your license or get upgraded if you're already licensed. So thanks very much for watching, and I'll look forward to the Q&A.